ELEC2 2019 question 1. Okay, so for question 1, part A, the state diagram for a sequence generator is shown in the diagram. The sequence is controlled by a 2 Hz clock. The sequence generator has been running for a while. How long does it take to complete each cycle of the main sequence? Now, as far as this question is concerned, the 2 Hz, what that tells us is that there's a frequency of 2 Hz, so it gives us the time to go from one state to the next. But the complete cycle of the main sequence is one complete loop from S0 back to S0 via S1, S2, S3, etc., etc. So what we need to do for the first part is to use that 2 Hz to find out the time it takes to go from one state to the next. And that's a fairly simple equation where we do 1 over f and that equals 1 over 2, and that gives us 0.5 seconds for each time we go from one state to the next. Okay, so how long does it take to do one complete cycle of the main sequence? Well, we've got 6 steps, so the total time is going to be 6 times 0.5, which is 3.0 seconds. Okay, part 2. States S6 and S7 are both unused. Explain the difference between them. Well, hopefully what you can see is S6 on the top left-hand part of our diagram is actually attached to S5, which is part of the main sequence. And that means this is called an unused state. And if accessed on power up or start up, what will happen is after one clock pulse, S6 progresses to S5, and therefore we get into the main sequence. And unused states always eventually lead to the main sequence. So our answer is an unused state. If accessed on power up, will progress towards the main sequence. S7 though is on its own on the right hand side and loops back to itself, and it never attaches to the main sequence, and this is called a stuck state. And stuck states never progress, and if accessed on startup, will never reach the main sequence. And there is our answer. Okay, B part 1. Part of the truth table for a different sequence generator is given below. Okay, so we've got a fair few gaps for DC and DA, but we need to remember how these particular truth tables work. That the next output becomes the new current output. So the output of the next output of state 0 becomes the new current output of state 1. So we should be able to progress backwards. So the current output of state 1 was the next output of state 0. So our 0, 1, 1 here, I'll say 0, 1, 0 here, was the next output of state 0. So we can put a 0, 1, 0 here. And the current output of state 2 is the next output of state 1. So we can put a 1 and it should be 0, 0. And we can progress down doing exactly the same for each of these. But we should notice that for state 4, we don't get the same. So for state 4, the next output doesn't become the current output of state 5, because that is where our main sequence ends, and then it becomes the current output of state 0. Okay, part 2. Write down a Boolean expression for DB in terms of CBA, then simplify so that it only uses 2 gates. Well, we've got the ability to do Boolean or to do a Carnot map, so I'm going to do Boolean first. So DB is only 2 highs for DB, and that's 1, 0, 1 and 1, 0, 0. So DB is equal to C and not B and A, or C and not B and not A. Now we can factorize this because we've got common C and not B. And put that outside the bracket. with A or not A in a bracket. Use our Boolean identity that A or not A is always a 1, and therefore we end up with C and not B and 1. And again, we're using our Boolean identities. Anything with and 1 is whatever it is. So our C and not B and 1 becomes C and not B. Or we could use our Carnell map. Now, in our Carnell map, C and not B and A is this part of our Carnell map. And C and not B and not A is the bottom left hand, so we should have a 0 and 1 here. And therefore, everything else is going to be zeros. We've only got one part of our Carnell map which we can join together to create an outcome, and that is C and not B. And so our answer, therefore, is that DB is equal to C and not B, and you have a choice as to which method you want to use. Okay, so the circuit diagram for the third sequence generator is shown below. Use this diagram to obtain a Boolean expression for DC, DB and DA in terms of C, B and A. Okay. So what we need to do is to look at the diagram, try and use the logic gates, but remember that we can also use the not Q outputs for each of the D types. So you've got DC on the left, DB in the middle, and DA on the right hand side. So if we look at DC first, DC is attached to not Q of A, so it's not A, so DC is not A. Okay, so for DB, DB has an AND gate attached to it, and the two inputs for those AND gates, one's attached to C and one's attached to A, so DB is C and A. And DA has a exclusive OR gate attached to it. That's attached to C and attached to B. Therefore, the Boolean expression is C exclusive OR B. Okay, so part 2. On power up, the system starts in the state C equals 1, B equals 0, A equals 1. So these are the attachments into to each of the outputs C, B and A. Then the clock then inputs one pulse. What state is the system now in? Now that clock input of one pulse means that via the logic gates, we're going to get those outputs going through the D types and outputting on the new CBA outputs. And what we need to realize is that D goes to Q on a clock pulse. Okay, so the easiest way probably to look at this is to think about if C equals 1, B equals 0, A equals 1, what does that mean in terms of DC, DB and DA using our Boolean expressions? So DC, remember, is not A. Well, if A is a 1, it's the not of 1, and the not of 1 is 0. Okay, so now if we do the same for DB, we know that DB is C and A. Well, that means it's 1 and 1 because C and A are both high. And when you have two 1s into an AND gate, the output is a 1. And finally, DC. DC is the exclusive OR of C and exclusive OR B. That means we've got a 1 exclusive ORed with a 0. And in the conditions for an exclusive OR gate, when we've got a 1 and a 0 on a 2-input exclusive OR gate, the output is high. Therefore, C is equal to 0, B is equal to 1, A is equal to 1. I'll just make sure that's A over here. And that concludes question 1 of ELEC2 to 2019.